We're starting section 17.3, the divergence theorem. So far, with the Stokes theorem and Green's theorem, there were a lot of similarities, and the discussion always was the relationship with the line integral over the boundary and the surface integral of the curl. Now, how about if we were basically talking about a solid? And so the divergence theorem comes in and relates a solid, which the boundary of the solid is going to be a surface, and to the basically the triple integral over the solid. And so here's the theorem: let S be a closed surface that encloses a solid W in R3. Assume that S is piecewise smooth and is oriented by normal vectors pointing outside W. So it's outward direction. Let F be a vector field whose domain contains W. Then the surface integral f ds over S is going to be equal to a triple integral over W of the divergence of F. This is just a your regular normal triple integral. It's just not nothing else to it, basically. And so again, I'm much more comfortable doing the triple integral of the divergence of F than doing a surface integral. And so that's the catch in here. Basically, it makes it a lot easier. So that said, how do I interpret this as a physical being? So basically what you're saying that you're adding up divergence at every point right here inside the solid. That's so you're adding up where the solid points of the solid that are source and points source of the basically the supply to other places, and you're subtracting the places that are taking stuff away from places. And so you're adding all those up to see how much is being supplied, how much is being consumed within the solid. And that's the right hand side. And then left hand side is saying that basically looking at the flux and telling you how much is getting out, minus in finding how much is getting out and how much is getting minus the stuff that are getting in. So basically whatever is inside is going to be equal to whatever is getting out. Whatever plus and minuses, whatever is inside providing or taking away is going to be equal to whatever the shell is emitting or getting in, which makes sense, right? And so that's the understanding of it. So the shell tells you how much is getting out and getting in, and the right hand side is that. And so that's the part of it. So first question. So example 1 is asking us find the flux of the vector field. So it's the flux, and again it's a contour flux because the surface is going to be closed surface. It contains a solid completely. There's no holes or anything in it. And so find this, the flux, and over the S, which S is the unit sphere, basically. Again, because I'm using the divergence theorem, I'm hoping, and it's a closed surface, and I'm finding the flux. So I'm hoping there's an easier way of doing this by taking the triple integral of the divergence of f. That is telling me how much is being created in there, how much is being, so unit sphere, and this one is, so that's S, that's the sphere, and I have to have the volume named something else. Let's call it W. So the solid inside is W. And so let's first of all find the divergence of F, and that's the partial respect to x of z plus partial respect to y of y plus partial respect to z of x, and that is equal to 1. So here this is equal to 1. Now the next part is I have to find the volume in there, and that is not too bad. See, the triple integral 1 dv. What is a triple integral of 1? Volume W. So what is volume W? W is that sphere. What is the volume of a sphere? 4 pi third of r to the r cubed, which is 1 to the power 3. And so it's 4 third pi. And that's it. So it was a lot easier than finding that surface integral, and that's the point of the theorem. So we saw the application when the divergence was equal to 1, and made it easier to find the volume. Now there's another one that makes it a lot easier, is that if the divergence is a constant c. So when a divergence is a constant c, c can come out of the integral. So when you're computing the divergence f dv, if that's equal to c, c can come out of the integral, and then you will have the volume sitting out there. So it would be 1 dv w. That part is the volume, so it's just c times the volume of w. We just discussed the when divergence is equal to a constant value, how to find the flux outside over a closed surface. Now let's do iClicker question 17.3a. Let S be a cube in positive octant with side length a bigger than 0 as shown. Which vector field has positive flux outward to S? So again, this is a cube, so it's a closed surface basically. So we're finding the if we're finding the flux, we're finding the contour flux of fds over the cube S. And now according, I give you 1 minute, maybe stop the video and come back. So according to the divergence theorem, this is going to be equal to triple integral of the divergence of f dv over the cube, and let's call the cube w over the solid inside. And so the divergence of f, if I'm computing the divergence of f, and divergence of f is a positive number, then basically that flux is going to be positive. See which one of these divergences are going to be positive. Divergence of A is going to be 0. Divergence of A is 0, 0. and not vector 0, and then divergence of B is equal to divergence of partial of x with respect to x is 1, partial of y with respect to y is 1, so again 0. Divergence of C is equal to partial of z with respect to z, which is 1, and here divergence of this one is just 0 plus 0 plus 0, so divergence of D is equal to 0. The only one with a non-zero divergence was C, and that makes the basically the triple integral over 1 dv, which is going to be the volume of D, which is a positive value, volume W, and that is a positive value. So C is the answer.